Hello! In today's video we're going to be taking a look at inverse matrices and then going on specifically to find the inverse of a 2 by 2 matrix, and on top of that we're also going to be taking a look at identity matrices, because you can't really have an understanding of what an inverse matrix is until you know what an identity matrix is. I'm also going to be assuming, if you're watching this video, that you know what a determinant of a matrix is, and if not, I do have a video going through the determinant of a 2 by 2 matrix that you can go ahead and watch, because that's going to come in useful for what we're doing today. So to get the ball rolling, let's start by explaining what an identity matrix is, and to get your head around that, we can actually take a trip back to numbers first, by thinking back to what the number 1 does when we're looking at multiplying. If we're multiplying anything by 1, it basically has no effect. Whatever number you multiplied 1 by ends up being the answer as well. And basically, an identity matrix has the same role for matrices and multiplication. If you multiply any matrix by the identity matrix, you end up with what you started with. So if we represent an identity matrix with the capital letter I, which is what we generally do by convention, then if you have another matrix A, then A times by I is guaranteed to be A, no matter what the matrix A is. And also, it does work the other way around, which is a bit controversial, because you might remember that normally when we're multiplying matrices together, it does matter what order you multiply them in, because you often get a different result, but not if one of the two matrices is an identity matrix, because I times by A will still be A. So there you go, that's what an identity matrix is. But what does it actually look like in terms of numbers in a matrix? Well, if you're looking at a 2 by 2 identity matrix, we often then specifically notate that as capital I with a little subscript of 2 there. And that would be a matrix with 1s in the main diagonal. That is the diagonal that goes from the top left to the bottom right. And then all the other numbers in the matrix are zeros. So we've got 2 zeros there and there. If you're looking at the 3 by 3 identity matrix, that would be represented by capital I subscript 3, and then that is again 1s in the main diagonal from the top left to the bottom right, and then all of the others are zeros. It's worth mentioning that this pattern then extends on if you do need to find the identity matrix for a 4 by 4 matrix, etc., etc. It's also worth pointing out that identity matrices can only be square matrices. So that means we are going to have the same number of rows as columns in our identity matrix. Okay, there you go. That's what an identity matrix is. And the reason that's important is going to be clear when we now take a look at what an inverse matrix is. In most cases, when it comes to numbers, we can both apply operations and also undo them. For instance, with multiplication, we could do 5 times by 2 equals 10, and then when it came to undoing it, we would actually have a couple of different options. One option would be to inverse the operation, that is, to find the operation that's the opposite of the operation you've done. So for instance, the opposite of multiplying is dividing, so if we wanted to undo times by 2, we'd divide by 2. Hence, 10 divided by 2, getting us back to where we started with 5. However, that's a bit of a problem when it comes to matrices, because we cannot divide by a matrix. So what do we have to do instead? Well, the other option we have when it comes to numbers is, instead of inversing the operation, we can inverse the number that we applied with the original operation. That is, if we're trying to undo times by 2, we can undo that by multiplying again by a different number. In this case, as it's specifically timesing by 2 that we're trying to undo, the number we have to multiply by to undo that is a half. So if we want to undo times by 2, we'll just times by a half. So therefore 10 times by a half does also get you back to the original answer of 5. But we've represented that same action in 2 different ways. This second option, though, is more a reflection of the sort of thing we end up having to do with matrices. We cannot divide by a matrix, but instead we can multiply by an inverse matrix if we want to undo the multiplication of another previous matrix. But what does that look like when we come to actually do this with matrices? Well, the first thing we need to be aware of is a bit of notation, and that is if you have a matrix A, we represent the inverse of matrix A with the notation A to the power of -1. That's quite nice because then that corresponds to other situations where the term inverse has appeared in mathematics, where that power of -1 has also been used in the notation to signify an inverse. This is important because then the inverse matrix has the following property. If you multiply the original matrix by its inverse, you are guaranteed to always get the identity matrix. And again, a special quirk of this is it doesn't matter what order you multiply the inverse and the original matrix in. Even though normally it does, in this case it doesn't. And either way, inverse times by the original matrix will always get the identity matrix. However, that only occurs if the original matrix and the identity matrix are right next to each other in the multiplication. There can't be another matrix in between the two of them as part of a much bigger, wider set of multiplications. So for instance, we do have to be careful if that's happening. For instance, if we have something like this, well, in this case, this can simplify. Because in this case we can see the B inverse and the B are right next to each other, so therefore those two things can combine to get I, and then A times by I is just going to be A, because the I is the identity matrix, and anything times by the identity matrix just gets the other matrix you're multiplying it by. But then if we look at the scenario where we've got B times by A times by B inverse, this time the B and the B inverse are not right next to each other, and therefore the properties we were looking at above cannot be applied. And so therefore in this case, unsatisfyingly, there's nothing we can do to simplify that expression. So that's something to watch out for when doing matrix algebra. And so putting these skills into practice already, we've got this situation if AB equals C, we need to rearrange to make A the subject of the equation. That's important because we then realize we therefore need to get rid of the B. As B is currently being multiplied by A, we're therefore going to undo that by multiplying by B inverse. But on top of that, we also know the B inverse has to be multiplied in a way that results in the B inverse being right next to the B. So that's important because it means we've got to do AB multiplied by B inverse. Now, when we do it in that order, we then also have to be careful when it comes to the other side of the equation, because we have to take note of which order we did the multiplication in on the previous side. Did we multiply the inverse at the front of the left-hand side, or did we multiply by it at the end of the left-hand side? Well, in this case, we multiplied by it on the end of the left-hand side. And that's important because whichever side you chose to multiply it by on the left-hand side is also the same side you have to multiply it by when you're coming over to look at the right-hand side. So in this case, as I chose to multiply by it at the end of the left-hand side, I've also got to multiply the end of the right-hand side by B inverse. And it's got to be in that order on the right-hand side. And that's because we're just going back to old school rules we're very familiar with by now. Whatever you do to one side of the equation, you have to do the exact same thing, the exact same action to the right-hand side of the equation. Now that we've done this, this is all very helpful because the B and the B inverse are next to each other, so we get the identity matrix. And of course then anything multiplied by the identity matrix is itself, so therefore we have now found the equation in a format that's rearranged to make A the subject of it. Okay, but then what happens if instead we were asked to make B the subject of the equation? Well, very similar idea, but this time we're going to need to multiply by A inverse, but we're therefore going to need to have the A inverse at the front if it's then going to be able to be next to the A in the AB. That's important though, because therefore that means this time I'm multiplying the front of the left-hand side. So that means when I'm going over to the right-hand side, I need to multiply the front of the right-hand side by A inverse as well. So this time it will be A inverse C on the right-hand side. That means we'll get IB equals A inverse C, and therefore B is equal to A inverse C. So therefore it's important you're aware of whether you're multiplying the front or the end of both sides of the equation each time. Whatever you do to the left-hand side, you have to do the same thing to the right-hand side. So that's how you use and apply inverse matrices, but how do you actually find an inverse matrix in order to be able to use it in the first place? Well, you basically need to remember a formula when it comes to finding inverse matrices for 2 by 2 matrices. And the formula is as follows. In front, you're going to have a factor of 1 divided by the determinant of the original matrix. And then inside, you need to remember the following rules. The elements on the main diagonal, the A and the D, swap places. And then the elements that normally, when you're finding a determinant, would be the ones you'd multiply and subtract from the other product. Those elements are going to be elements that now have a negative sign in front of them, but they do stay in the same place. So the main diagonal, they swap places. The other diagonal, you just put a minus sign in front of them. Cool. Things to be aware of. That formula is not in the form booklet, so you do need to remember that off by heart. Bit of a pain early on, but the more you use this stuff, of course, you start to get familiar with it and it becomes second nature. Okay then, let's take a look at doing that in practice. So we need to find the inverse matrix for this matrix. Well, in order to do that, we first need to know the determinant. So working out the determinant of 1, 2, 3, 4, that's going to be 1 times by 4, which is 4, take away 2 times by 3, which is 6, and that's minus 2. So therefore, out the front, we're going to have a factor of minus a half, and then the matrix inside, the 1 and the 4 will switch places, and then the 2 and the 3 will have a minus sign put in front of them. Or in other words, I should have reworded that on the previous slide as multiplying those numbers by minus 1. In other words, if they're already a minus, they would actually become a plus. Okay, now in this particular case, you are welcome to leave that factor of minus half out the front of the matrix, and in most cases that's easier if you do leave it in that format. But if you want, you can absorb that factor inside. So basically what that means is I've got to times all the elements inside the matrix by minus a half. So therefore that means another way I could rewrite this answer is it would get us minus 2, positive 1, positive 3 over 2, and minus a half. So that's another way of writing that same inverse matrix. It's worth mentioning that you can use a calculator to find an inverse matrix. And indeed, you are allowed to do this for the exam board that I teach. However, you do still need to know the formula that we just looked at, because they always have ways of being able to force you to do so. Namely, they've just got to put algebra anywhere inside the matrix, and then all of a sudden the calculator won't be able to deal with it. So therefore, it is important you get used to using a formula so that you are still able to do all questions involving a 2 by 2 inverse. Hopefully you found this video useful. I will see you in a future video, maybe on matrices, maybe on something else. Goodbye.